G'day, today we're going to talk about the second part of section 3.3, the idea of zeros and factors of polynomials. And we're going to pick up from where we left off. Last time we discussed the factor theorem and the complete factorization theorem. And we looked at the fundamental theorem of algebra. And if you remember, the fundamental theorem of algebra told us that every polynomial of degree n has n zeros. So here's an example. Let's start with a quite simple example in this case. This is a quadratic. We're quite good at dealing with quadratics. We can write this in its standard form. So I could complete the square on it. Half of that -6 is -3. So this is going to come out to be x minus 3 all squared. When I expand that, I get x squared minus 6x plus 9. And so there's one missing here. And so the standard form of this quadratic is simply x minus 3 all squared plus 1. We know quadratics well, so we can obviously sketch a graph pretty quickly. If you calculate the y-intercept here, this is going to be 10. The vertex is here at 3, 1. We can just read that off the standard form. Okay, so what are the zeros of this function? Where is this function equal to 0? And we can quite clearly see from the graph that this function has no real zeros. If the function is 0 at a real number x, then f of x would be equal to 0. And in this case, f of x is never equal to 0. For a real value of x. If it was 0, this function would pass through the x-axis. In this case, it never passes through the x-axis. The minimum value of this function is here at 3. So this function's also, x equals 3, but the function itself is always bigger than or equal to 1. It's never 0. And so there are no real x's, and so there are no zeros of this function. But we had the fundamental theorem that told us that every nth degree polynomial, and here we have a degree 2 polynomial, has n zeros. So in this case, we expect 2 zeros. So what's going on? Well, let's try and solve the equation. If we try and set the function equal to 0 here, let's take it in its factored form. If we set this equation equal to 0, then we can solve it, but we run into a problem. And that problem you can see here is that the square of a number is equal to -1. And we know that when we square a real number, we always end up with a positive. And so this has no real solutions. Well, that doesn't surprise us because we know there are no real values of x that make this true. So to make progress, we're going to have to use complex numbers. So we define an imaginary number. That imaginary number is the square root of -1. We know there's no real number that has the property that it's equal to the square root of -1, because if we had a real number that was equal to the square root of -1, then we could square that number. We'd take I squared, and that would be the square root of -1 times the square root of -1, and that would be -1. In other words, if I write it more neatly, the I squared would equal -1. And if I squared is equal to -1, well, I can't be real, because we know no real number has that property. But this lets us make progress on our problem. Let's go back to this problem we were trying to solve. If I say that x minus 3 all squared is -1, well, I know that -1 is the same as I squared. I invented this imaginary number, we'll call it I squared, and that means we can now undo the squaring using the square root, and that tells us that x minus 3 must be plus or minus I, because this squared was I squared, so this must be either I or minus I. And that lets us solve it completely by adding 3 to both sides. X is equal to 3 plus or minus I. We've got two solutions here, and that's what we expect. So these are the two zeros. There are 2 zeros for this polynomial, but they are not real. That lets us write the complete factorization. And we know the complete factorization just comes from, well, the factors are always of the form x minus c, where c is a 0. And we have 2 zeros. They're 3 plus I and 3 minus I. So there's x minus c1 and x minus c2, if you like. X minus 3 plus I, x minus 3 minus I. This is the complete factorization. There's a 1 in front of the f here, and so there's a 1 out the front. That doesn't make any difference. I don't need to write it. We've solved this factorization problem, and we see that we didn't mention last time the complete factorization theorem may involve complex zeros. So they won't appear on the graph, but they are zeros. So I said earlier, every x-intercept is a 0, but not every 0 is an x-intercept, and that's what we see here. We have several zeros that are complex, and therefore they're not on this, because this is literally the real line. Along the x-axis, all we're doing is writing all the possible real numbers. And so we've got 2 zeros that aren't real numbers, so they can't possibly be along the x-axis. Let's look briefly at the properties of complex numbers. So I'm just going to take two complex numbers here and think about how we can combine them. We can add complex numbers. So I've got two complex numbers here, 3 minus 4i, minus 2 plus 7i. And we can literally add them. We add the real and imaginary parts. So just writing this down, we're literally adding this thing by adding the real parts, and the real parts is a 3 here and an imaginary part here. So the 3 and the minus 2 are added together. And that gives us the real part of this imaginary number. And then we add the imaginary parts, the minus 4 and the 7. So I've got minus 4i and 7i. I'm literally treating that I as just something that floats around. And so I've overall got 1, what's that, plus 3i. So when I add those two numbers, I get 1 plus 3i. I can multiply these imaginary numbers, z times w. That will give us, multiplying this out, we'll have to use multiplying all the terms. We get 3 times minus 2, that's minus 6. And then we'll get plus 3 sevens, that's 21i, minus 2, let's make that a bit bigger, minus 2 times minus 4 sounds like positive 8i, and then minus 4i times 7i, or 4 sevens are 28, I think, although that's a negative. So 4 sevens are 28, we get negative 28, but there's two i's, so negative 28i squared, negative 28i squared. And remember, our fundamental property of complex numbers is that I squared is minus 1. So this is minus 6. We're going to have 21 plus 8, that sounds like 29i, and then we're going to be having 28 times minus 1, because I squared is minus 1. So this is 28, I'm subtracting 6, so overall this is 22 plus 29i, because this turns back into a real number. And then I combine it with a negative 6. The one, you can also divide complex numbers. And perhaps the most useful thing we're going to deal with is the idea of complex conjugates, which is represented with a bar. And we just take a number. If we've got a complex number, z is a plus b, I, and again I was using this terminology, a is the real part, b here is the imaginary part, so this is the imaginary part, b and a is the real part. We can just, in our example, we had 3 minus 4i. 3 is the real part, negative 4 is the imaginary part. If we want the complex conjugate of 3 minus 4i, we just change the sign. The complex conjugate is 3 plus 4i. And if we're looking at minus 2 plus 7i, then the complex conjugate of w, we use the bar over it to represent the complex conjugate. But the complex conjugate of minus 2 plus 7i is minus 2 minus 7i. And that's basically the properties of complex numbers that we need. We saw in our initial example that we could take a quadratic in that case, and although it had no real zeros, we could find complex zeros. And in this case, the complex zeros were 3 plus I and 3 minus I. I'm just reading off the complete factorization we have here. And you'll notice that these two things are the complex conjugate of each other. If we take 3 plus I, the conjugate of that is 3 minus I. If we started with 3 minus I, the conjugate is plus 3i. And so this is an example of an important theorem, which is shockingly known as the complex conjugate theorem. And it simply says that if you've got a polynomial that has a complex zero, just like this case, if it's got a complex zero and the complex part's not zero, the b part is not zero, then the conjugate of that number is also a zero. So in this case, if I had told you that 3 plus I is a zero, this theorem would have told us immediately that 3 minus I is a zero. If I'd told you that 3 minus I is a zero, then this theorem immediately tells you that 3 plus I is also a zero. And if we've got zeros by the factor theorem, we've also got factors. So this is really powerful when it comes to factorizing polynomials. So let's use that to actually work out a problem. Here's a polynomial. X cubed minus 2x squared plus 12x plus 40. And we're told that 2 plus 4i is in fact a zero of the function. And you could check that, right? I'm not going to check that because it sounds awful, but we could check it by literally calculating f of 2 plus 4i. And multiplying all of that out, you would get some horrible mess, but eventually, hopefully, you could show that that was zero. So let's just take it for given that this is true, and that tells us that 2 plus 4i is, well, wait for it, it must be a zero, because it makes the function zero. This is precisely what it means to be a zero of a function. So 2 plus 4i is a zero. That means, let's call it z. It's a complex zero. That means z bar, according to the complex conjugate theorem, is also a zero. So 2 minus 4i is also a theorem. So not a theorem, is also a zero. So using what we saw in the previous examples, I could take the factors. So that tells us that f has factors given from those two zeros. So each zero corresponds to a factor, x minus c. I've just put the two things there. Using our previous examples, we could simply divide this polynomial, the f that we're given, by each of those. And then what we'll be left with, well, this is linear, this is cubic. So after we divide out those two factors, we must be left with a final linear term. We could do that, but we'd have to divide with complex numbers, and long division is complicated enough to begin with. So let's actually simplify this first. Let's take the fact that these two things are zeros and simplify the factor. Notice that when I look at this polynomial f, there are no i's here. These are all real numbers, and if you remember the way we write polynomials, we're only interested in the coefficients being real. So 1x cubed, minus 2x squared, 12x, and 40. They're all real numbers. They have to be real numbers. So when these two things have been multiplied out, there shouldn't be any i's left because there are no i's in f. So let's calculate this product to see what factor f will have overall. That is literally, let's just multiply these things together. And I'm going to multiply all the terms out, and I'm going to keep these things grouped for now. So we're going to have an x times an x from here multiplied by the 2 minus 4i over there. We're going to have another term that has an x from the second term, and then a 2 plus 4i from the first term. And then the last term is just going to be a product of those two factors, and it's going to be positive. It'll be 2 plus 4i, 2 minus 4i. And so when we multiply all of that together, we'll get something that is a factor of f, because the fact that each of these are zeros means that each of these is factors of f, and so the product of them should also be a factor of f. And we can simplify this. If you look at these terms, so I don't have to write it all out, look at these terms. There's a minus 2x here, and there's a minus 2x here, right? There's a minus 2x there and a minus 2x there. And when I distribute the x in here, I get plus 4i, and I distribute the x in here, when I distribute there, I get plus 4i, that's right. When I distribute it here, I get minus 4i, and they cancel. So those two terms cancel each other. And so as we start multiplying this thing out to get all of the terms, we're going to get 2x from this one, 2x from this one, and so we're going to left with minus 4x. And then we've got this final term. So let's write that out. When I, again, multiply that out, we'll get 2 times 2, which is 4. And then we'll get 4i times 2, which is 8i. And then we'll get 2 times minus 4i, which is minus 8i. These will always happen. This will always cancel. And then we're left with minus 16i squared. And notice again that those 8i's are going to cancel. And we know what I squared is. I squared is minus 1. And so putting this together, we get x squared minus 4x plus 4. That's this piece. The 8i's cancel. And this is minus 16 times minus 1. Because we're using the key fact about complex numbers, I squared is minus 1. And so multiplying all of this out gives us x squared minus 4x. Well, we've got 4 and we're adding 16, so this is plus 20. And this thing is also a factor of f. And so just recapping what we did on the previous page, this polynomial we started with, this cubic, we found that it has two zeros. They were complex zeros, that was all right. And we calculated the product of those two complex zeros, those two complex factors that corresponded to the zeros, and we found this factor. And this must divide f. And if it divides f, we can divide it out. And so I'm just going to do a long division just as we've done before. I'm going to multiply this x in. We'll get x cubed minus 4x squared plus 20x. And we cancel that, and we're going to be left with 2x squared minus 6x, minus 8x. And then I'm going to drop the 40 down, and then I'm going to multiply everything by 2. That gives us 2x squared minus 8x plus 40. And that's what we expect, because we better get a remainder of 0 here, because I'm claiming this thing is a factor. And if it's a factor, when I divide, the remainder has to be 0. And that has allowed us to completely factorize the function f. Because when we did that long division, we found the quotient, oops, that's meant to be a a line. We found the remainder. Well, the remainder was 0. There's the quotient, and there's the thing we divided by. And we already know how to factor the thing we divided by because it came from the knowledge of zeros. And what we're left with is this complete factorization of the function f. This is a third-degree polynomial. The leading coefficient here is 1, so I know we should have a 1 out the front, which we do. And we get the factors that come from knowledge of the complex zeros. And then once we divided that out of the polynomial, we were left with this quotient term, a remainder of 0, and so we get the complete factorization of f. And what we've used here to find this is the conjugate zeros theorem. We were given a single zero of this polynomial, but that zero was complex. And so as soon as we have one complex zero, we have two complex zeros. Two complex zeros give us two factors. Two factors let us get a real valued polynomial, no, a real coefficient polynomial here. And I could divide that out. So I just divided the quadratic we got through the x cubed and found the remaining factors. So together with the complete factorization theorem and the factor theorem and the remainder theorem and the division algorithm, the conjugate zero theorem allows us to factorize all polynomials. We've seen over the last few videos how to factorize any nth degree polynomial using all of those theorems. So have a go at the pre-class homework, and I will see you soon to explore these ideas further.